For the case of designing a grid-connected PV system based on yearly energy requirement, it includes several equations that are related to the parameters from the PV module, cable, and inverter. So this is an example of PV modules, and the other side is the inverter. So both devices are connected through the DC cable. The DC cable is the route for the current to be flowed from the PV modules to the inverter, and then after the inverter, the AC voltage will become up. Okay. In these PV modules, since we already know PV modules means we have more than one module, so 2, 3, 4, 5, 6, and so on modules. So each module have their own PMP STC, as we learned before. And also in this case also we can also call as P module STC. So all these modules when combined or connected in series or parallel, you're going to get one value, we call that as P area STC, where the P area STC is the multiplications of total numbers of the modules to the P mod STC for each module. For example, we have a single module with 100 watt, so and then we have the 10 modules connected in series, means that 10 multiplied with 100 watt are going to get 1000 watts. This is the meaning. Next, from the PV modules, there are several, we call that as degradation factors, or we call that as derating factors. There's three items here, where the first one is FMM. What is the FMM? FMM is the derating factor for manufacturer tolerance and mismatch. Remember, we have learned on the previous slide. So the manufacturing tolerance is part of the subsystem losses. So this is it. So the FMM is a derating factor coming from the manufacturing tolerance. Next, the F-temp. What is the F-temp? F-temp is the derating factor for temperature effect. Okay, temperature effect. So this is the derating factor for temperature. Next is the F-dirt, derating factor for dirt. Okay, derating factor for dirt. So this is the derating factors that exist on the part of PV modules, where the combination between the P area STC and these three items form a PV array, where the second equation coming out, which is the P array equal P array STC multiplied with FMM multiplied with F10 multiplied with Fdet. Okay, we finish for the second part. In the third part, clearly this is the sun. It means that the PV modules receiving sunlight or receiving a solar irradiation. So the PSHPA, paid sun hours, PA is the per annual. So PSH for expected angle for 1 year. So this is the value that I mentioned in the previous slide. Like I told you, if you 1 day we get 4 hours, in a month we get 120 hours, and in a year, in approximation, we get 1440 hours. So this is that value. Means that the combination between the P array and the PSHPA will form EPV. EPV is the energy generated through the PV modules, where P array equal to PSHPA. Okay, we finish on the PV module part. Now we are traveling to the inverter through the highway. Where's the highway? Is this cable. During the highway, we have toll. What is toll? This MPV inverter or efficiency. This is the efficiency, a symbol of efficiency, PV inverter. If we check here, cabling efficiency between the PV and the inverter. Cabling efficiency is closely related to the voltage drop. Let's say our voltage drop is 3%. So it means that the efficiency for the cable between the PV and the inverter is 0.97, like that. Okay. Then after that, we reach at the place of the inverter. So in the inverter itself, they have the efficiency. Okay, the efficiency, I told you, it may varies from 92 to 97%. In average part, sometimes it is 95%. So this two combination will form another equation, efficiency of PV and SS. Okay, PVSS is the multiplication between these two items. And finally, the result. The result, we call that as E system, or this is the energy requirement or energy yield, which comes from the EPV, the left side multiplication with the efficiency of PPSS. So this is the total value that we get for the annual energy yield, comes from all the parameters